Hello and welcome to IP lesson. In this lesson, we will learn about data link layer. Let's start with switch. Switch is a device that operates in data link layer of TCP/IP module. The switch is a device that sharing resources by connecting in the devices together. For that reason, the switch is the nearest device to our end devices, to our PC, printer, and any end device. The switch is a device include many ports because, as we mentioned, it connects end devices together. Unlike router, the router will be the nearest device to the WAN connection or to the outside network. For that reason, the router doesn't include many ports, unlike the switch. The switch ports are up by default, so we don't need to do any configuration in order to turn on the interfaces, unlike the router. For router, we need to enable the interfaces or turn on the interfaces in order to work. So the switching is a mechanism in a computer network that helps in deciding the best route for data transmission if there are multiple paths in the network. So let's see how our switch will forward the data. Let's take a look at our example. In our example, we have James PC, Mary PC, and between those two PCs, we have two switches. James PC MAC address is all A and Mary MAC address is all B. When James wants to send the data to Mary, it will start the encapsulation process and every single header will add its own feature to the data. As soon as the data will arrive to the data link layer, the data link layer will include the source MAC address, which is James MAC address, and the destination MAC address, which is Mary MAC address, and then forwards the data to the switch. Our switch will be careless about application transport network layers, so the switch here need to forward the data to the recipient, and it doesn't need to know what type of data is that. For that reason, our switch will decapsulate the physical and the data link layer, and in the data link layer, it will see the source MAC address and the destination MAC address, which is Mary MAC address, and forwards the data. The second switch will do the same thing and will take a look at the source MAC address, destination MAC address in order to be able to forward the data. Then the data will arrive to Mary and Mary can read the data. So let's ask a question here. How our switch knows that Mary MAC address is connected through interface fast Ethernet 0/3? And the answer for this question is that our switch uses something called MAC address table. Inside that MAC address table, it has the device, and next to the device, the interface where is that device connected to. For example, James connected to interface fast Ethernet 0/1, Robert connected through interface fast Ethernet 0/2, and Mary connected through interface fast Ethernet 0/3. For sure, our switch doesn't know the users that is connected to that interface, so instead of using the name of the user, it uses the MAC address. So as we can see, James MAC address connected to interface fast Ethernet 0/1, Robert MAC address connected through interface fast Ethernet 0/2, and Mary MAC address connected through interface fast Ethernet 0/3. So when James wants to send data to Mary, the source MAC address will be James MAC address, the destination MAC address will be Mary MAC address. Our switch will look at the MAC address table and find Mary MAC address connected through interface fast Ethernet 0/3. Our switch will forward this frame to interface fast Ethernet 0/3, and the data will arrive to the correct recipient. So all is good so far, but what about the MAC address table? Is our device comes with all the MAC addresses included on the MAC address table? And the answer is no. Our switch use a dynamic MAC address learning in order to learn about the MAC addresses. For the dynamic MAC address learning, we will use two examples. Example 1, if our PC knows the destination MAC address. And the second example, if our PC doesn't know the destination MAC address of the recipient. In the first example, our switch will do something called flooding. So let's look again at our topology in order to understand what is the flooding and what will happen. So in our topology, we have James PC, Mary PC, and Robert PC. James MAC address is all A, Mary MAC address is all B, and Robert MAC address is all C. James wants to send data to Mary, so the data will exit out of James PC with the source MAC address, James MAC address, and the destination MAC address is Mary MAC address. First, the dynamic MAC address learning will take advantage of this data and will look at the source MAC address, which is James MAC address, and will add an entry on the MAC address table for James MAC address. After that, our switch will look at the destination MAC address and there is no entry for that destination MAC address. In that case, our switch will do flooding. So flooding is forwarding the frame to all possible receivers except the one it came from. So the data came from interface fast Ethernet 0/1, and our switch is smart enough to know that this interface doesn't have the destination. So it will flood the data, it will send it to interface fast Ethernet 0/3 and interface fast Ethernet 0/2, asking the PCs, are you the device with the MAC address all B? Robert will ignore this data because it's not meant to him. And Mary will reply to this data and saying that this MAC address belonged to her. Same thing will happen. Our switch will look at the source MAC address and save an entry for that MAC address on the MAC address table. And after that, James can send the data to Mary since we have James MAC address on the MAC address table and the Mary MAC address on the MAC address table. So you can ask a question here. How James PC knows the destination MAC address and our switch doesn't know the destination MAC address? And the answer is that our PC have a MAC address table and it uses it in order to learn the MAC addresses similar to our switches. So let's see our second example. In our example, James PC doesn't know the destination MAC address. In that case, the data cannot exit out with no destination MAC address, and our PC will use the broadcast MAC address. The broadcast MAC address is all F, and this MAC address cannot be configured in any end device. So all the network devices know that the MAC address with all F is a broadcast MAC address. As soon as the data will arrive to our switch know that this is a broadcast MAC address and it will do a broadcast. So broadcast is also similar to the flooding, which is forwarding the data to all the interfaces except the one it came from. But broadcast is a general term, so we can say broadcast for router, we can say it for switch. Unlike flooding, flooding is a term just for the switch. So back to our example. In our example, our switch will do a broadcast. And let's ask a question here. How Mary can identify that this data meant to her, since the destination MAC address is a broadcast MAC address, not Mary PC MAC address? And the answer will be the IP address. So when the data will arrive to Mary PC, Mary will start to decapsulate the data and look at the destination IP address and find her IP address on the network layer. After that, Mary will reply to this message and our switch will take advantage of this data and put entry for Mary MAC address. This is how our switch learns the MAC addresses dynamically. So here another example. James also went to send the data to Mary, but right now we have more than one switch. In that case, our switch will learn about Mary PC and Robert PC through the connected switch. So our switch will put an entry if you want to forward this data, forward it through interface fast Ethernet 0/3, which is connected to the second switch. And Mary and Robert are connected directly to the second switch, and the data can be forwarded to Mary. So after we connect our devices to our switch, what about if one device disconnected? What about the MAC address table? Is the MAC address table will keep that device MAC address on the MAC address table? And the answer is no. The MAC address use something called aging time, and the aging time is the maximum amount of time that a MAC address remain in the MAC address table, and by default it's 300 seconds or 5 minutes. So after our switch learn about Robert MAC address, it will start to count the 300 seconds. After that time, Robert MAC address will be removed from the MAC address table. Let's imagine if that was a bad cable and we connect Robert PC again to our network. In that case, our switch will start the dynamic MAC address learning process from the beginning in order to learn again about Robert MAC address. Next we have the Ethernet frame, which is IEEE 802.3, and as we mentioned before, the data on each layer looks different than the other layers. So we have another measurement which is byte, so the 1 byte equals 8 bits, and this is just a different measurement unit. It's similar to 1 hour equals 6 minutes. So we have 7 bytes for preamble, 1 byte for SFD, 6 bytes for destination MAC address, 6 bytes for the source MAC address, 2 bytes for types, and from 46 to 1500 bytes for data and bed, and we have also 4 bytes for FCS. So the last thing added to the data is the FCS. Is that everything that we can see on data link layer? And the answer is no. It's all depend on the protocols and the encapsulation that we are using between our devices. For example, if we are using a protocol called trunking protocol using encapsulation 802.1q, we can see another field called the VLAN tag. So let's take a look at more details about those fields. Preamble, allow sender and receiver, establish synchronization. SFD is a start frame delimiter, and it indicates that the upcoming bits are starting of the frame. Destination MAC address, the MAC address of recipient. Source MAC address of the sender. We have type defines the type of protocol of the upper layer, so this refers to the network layer. So type refer to the type of protocol used on the network layer. Is it IP version 4, IP version 6, or is it ARP? Data and bed. This is the data coming from other layers, and bedding are added to the data if the data smaller than the minimum acceptable size. FCS is a frame check sequence. The sender apply a complex math formula to the frame before sending it, then the receiver does the same formula and compares the data to detect NIC or cable problem cause data corruption. So as we mentioned, SFD or start frame delimiter indicates that the upcoming bits are actual data and not a random noise. So the SFD kind of alarm referring that this is actual data. Next we have the FCS or frame check sequence. So when the sender has the data ready, The FCS will apply a complex formula. The most famous formula for that is CRC, or cycle redundancy check, and after it will apply this formula, it will give it a result. Let's imagine that the result is X. The receiver will receive the data and it will apply the same formula. If the result is X, that will indicate that there is no corruption happened to the data during the transferring. If the result is not the same, this will indicate that there is a problem with the physical layer, a problem with the NIC card, or a problem with the cable itself. Next we have padding and fragmentation. So the normal size of the data should be minimum 46 bytes and the maximum 1500 bytes. The maximum size is something called MTU, or maximum transmission unit. So the data cannot be less than 46 bytes and it can't be larger than 1500 bytes. If the data smaller than 46 bytes, we will add a padding to the data, and the padding is just a filler. It's all zero in order to meet the minimum required size. If the data is larger than 1500 bytes, fragmentation will happen, and the fragmentation is not good, and also fragmentation happen on network layer and the data link layer. So the main component of data link layer is the MAC address. The MAC address stands for Media Access Control Address. Also some people call it BIA, or Burned In Address, and the reason of that, because the MAC address encoded or burned into the ROM chip on the NIC card. Some people also call it physical address. The MAC address is 48 bits or 6 bytes written in 12 hexadecimal. The first 24 bits is something called OUI, or Organization Unique Identifier, and the last 24 bits is something called Vendor Assigned. The MAC address is globally unique. You cannot find two devices have the same MAC address. This is an example of the MAC address. So the MAC address can be 4 hexadecimal dot 4 hexadecimal dot 4 hexadecimal, or it can be written on that format also. So for hexadecimal, we don't need to know that much about it, but this is the hexadecimal, and this is our regular number. So for 10 we have A, for 11 we have B, for 12 we have C, for 13 we have D, for 14 we have E, and we have F for 15. So what is OUI and what is vendor assigned? So first of all, the IEEE is a company that provide the OUI, the Organization Unique Identifier, and if company like Dell or HP want to manufacture some NIC devices, they have to require OUI from IEEE. IEEE will give Dell a unique OUI and will give HP a unique OUI. After that, the company can assign any vendor assigned value to the MAC address. So when transmitting the data, we can send the data unicast, multicast, or broadcast. Let's start with unicast. Unicast is a single sender to a single receiver. Let's take a look at our topology. In our topology, our switch learned already about the devices that is connected to it. So when James wants to send the data to Mary, the data will go directly to Mary. So this is called unicast, single sender to single receiver. Next we have the broadcast, and the broadcast is a single sender to all possible receiver. We spoke already about the broadcast, and we said that if the destination MAC address unknown, the MAC address will be all F, which is the broadcast address, and in that case, the data will be sent to all the interfaces. This is called broadcast. We have also the multicast. The multicast is a single sender to multiple receivers. Let's take a look at our example to understand this. In our example, we have router 1, router 2, router 4, router 5. Those routers using a protocol called OSPF, and we have also router 3, and this router doesn't use OSPF. If router 1 want to send the data to the devices that using the OSPF, the data will be sent through the multicast address, and in that case, only the devices that is using the OSPF will receive this message. This is called multicast. When transmitting the data, we can send it as a half-duplex or we can send it as a full-duplex. So half-duplex is a device cannot send data and receive data at the same time. Similar to that is the walkie-talkie. If you are using the walkie-talkie, you can speak or listen, but you cannot speak and listen at the same time. This is called half-duplex. We have also the full duplex. Full duplex is sending and receiving data simultaneously. Example of that is the cell phone. So when you speak at the cell phone, you can speak and listen at the same time. Before the switch, there was a device called a hub that was using instead of the switch. The hub is a device that forwards the data using the physical layer, so it doesn't use MAC address table in order to forward the data. If the data came to the hub through one interface, it will forward the data to all the interfaces regardless the source MAC address or the destination MAC address. The hub is always half duplex. For that reason, the hub use something called SISMA CD, which is carrier sense multiple access with collision detection in order to avoid any collision on the network. So it have to confirm first that there is no transmission happen on the data before it start to send the data to all the interfaces. So the hub used to be a half duplex and it used the SISMA CD because when a frame ready, the hub check if the channel is busy. If the channel is busy, it will wait until the channel become idle. So currently, it's very rare to find a hub in a network, but we have to put on consideration if we have a hub on our network, we have to configure the interface that is connected to that hub as a half duplex. This is the end for this video. Thank you for watching and see you in the next one.